In the previous chapters, we have studied about different platforms, the advantages and application. Most of the remote sensing instruments such as sensors are designed to measure photons. Fundamentally to this operation is a device known as detector which works to measure radiation. Radiation is nothing but a beam of photons on the basis of the photoelectric effect. When a light sensitive material is subjected to a beam of photons, the electrical energy is released and this energy is proportional to the amount of incoming radiation. A sensor thus provides a means of measuring radiation. This basic mode of operation is common to each of the sensors considered here. In this chapter, we will discuss about the sensor system which are present on the platform. Sensors. The sensor system functions as the satellite that record the scene. It is similar to the eye of the human beings. Sensor is an electronic circuit which can record the electromagnetic radiation incident upon it. Sensor is a device comprising of optical component or system and a detector with electronic circuit. It senses a variation in input energy to produce a variation in another or same form of energy. All sensors employed on the Earth observation platform is electromagnetic radiation to observe Earth features. We know that solar radiation is a main source of electromagnetic radiation and it is combination of several wavelengths such as gamma rays, X-rays, visible, infrared, thermal and microwaves. The first issue to be considered in selecting the sensor is the scale. Terrestrial and airborne sensors have high spatial resolution, but sensors on satellite are having relatively coarser spatial resolution. There are two types of scales, that is large scale and small scale. Based on the criteria to be addressed for using high localized large scale sensors are utilized, whereas for refined and more regional and coarse sensors with small scale are used. Thus, scale determines the major part in selecting which type of sensor is to be mounted on which type of platform. Sensor systems mainly operate in visible, infrared, thermal and microwave regions of electromagnetic radiation. Remote sensing sensors measure radiation of objects under the study in a given wavelength. They comprise of several components such as systems to receive the radiation from the pixel and a telescope, calibration source and a spectrometer, amplifier and recording system. There are different types of classification of sensors such as imaging versus non-imaging, passive versus active. Imaging sensors. Remote sensing data are the recorded representation of radiation reflected or emitted from an area or an object. When measuring the reflected or emitted energy, either images or non-imaging sensors can be used. Data from the imaging sensor can be processed to produce an image of an area, within which small parts of the sensor whole view or resolved visually. Image data provide an opportunity to look at spatial relationships of objects, shapes and estimate physical size based on the data spatial resolution and sampling. Then spatial information is needed such as mapped output image data are used. Non-imaging sensors. Non-imaging sensors usually are handheld devices that registered only a single response value with no final resolution than the whole area viewed by the sensor, and therefore no image can be made from the data. This single value can be referred to as a type of point data. However, some small area is typically involved depending on the sensor spatial resolution. In contrast with imaging sensor, this type of sensor does not record how the input varies across the field of view. In the remote sensing field, the commonly used non-imaging sensors include radiometer, altimeter, spectrometer, spectroradiometer and LiDAR. Radiometer. It is used to measure the amount of electromagnetic energy present within a specific wavelength range. It is operational in ultraviolet, infrared and microwave bands of electromagnetic radiation. It is used in calculating various surface and atmospheric parameters. Altimeter. It is an instrument used to measure the altitude of an object above a fixed level. It is operational in infrared, microwave and radio wave sonic bands. Its application is mainly seen in mapping ocean surface topography and the hills and valleys of the sea surface. Spectrometer. It is an instrument used to measure the spatial content of an incident electromagnetic radiation. It is operational in bands of visible, infrared and microwaves. It is used in multispectral and hyperspectral imaging. Spectroradiometer. It is an instrument used to measure the intensity of the radiation in multiple spectrums. It functions in the bands of visible, infrared and microwave. It is used in monitoring sea surface temperature, cloud characteristics, color, vegetation, chemical species in the atmosphere. Sonar. It is used to measure the distance of an object or determine the depth of the water beneath the ships and boats. It uses acoustic band of the electromagnetic spectrum. It is used in navigation, communication and security, underwater object detection, for example, handheld sonar for a diver. Radio acoustic sounding system. This instrument uses radio wave and acoustic waves. It is used for measuring atmospheric lapse rate while using backscattering of radio waves from an acoustic wavefront to measure the speed of the sound at various heights above the ground. It is added to the radar wind profile or the sonar system. Passive remote sensing. Passive sensors measure light reflected or emitted naturally from the surface and the objects. Such instruments merely observe and depends primarily on solar energy as the ultimate radiation source, illuminating surface and objects. Therefore, except for the thermal sensor, they cannot be used at the night time. Thus, in passive sensing, there is no control over the source of the electromagnetic radiation. Fixed physical properties of substance being measured Earth in are used to find measurements frequency bands for passive sensors. These fixed properties are also reflected as molecular resonance. It is noticeable that frequency does never change and associate values cannot be duplicated with other frequencies present in the band. Radio astronomy instruments are used to pattern the objects required from passive sensors. These low frequencies are quite sensitive to accumulation radiation, especially that comes from the radiation generating through located on the ground. In such criteria, both in-band and out-band frequencies are involved in which measurements are being made. Passive sensors are most commonly sensor type used in vegetation related remote sensing. This is not only because passive sensor systems are generally simpler in design, but also because portions of the solar spectrum provides very useful information for monitoring plant and canopy properties. Passive remote sensing is preferred for satellite imagery since it delivers excellent image in quality through technologies such as hyperspectral and in multispectral, unlike the active remote sensing. Passive remote sensing offers less noise control as the source of the energy is primarily sun and it is out of control of the surveyor. Passive remote sensing delivers less accurate measurement readings of the ground objects due to the variation in sunlight affected by the weather conditions. Passive remote sensing uses radiation signals from old satellites that are easily to operate and also focuses on land use, land cover analysis and small scale mapping requirements. Passive remote sensing has small datasets collected and does not allow for detailed interpretation of information acquired. Passive remote sensing follows geostationary orbits position over exact location in time. It is sensitive to weather condition which may affect accurate measurements of temperature. A major limitation of passive system is that the most cases that require sunlight in order to valid in useful data to be acquired. Consequently, Deployment of data acquisition by passive sensor vary depending on lightning and weather conditions, since cloud cover can interfere with the path of the solar radiation from the sun to the surface and then to the sensor. The signals detected by passive sensors can be generally altered due to the atmospheric effect, especially in the shorter wavelength of the solar spectrum that are strongly scattered by the atmosphere. These effects can be minimized by collecting data only under very clear and dry atmospheric conditions. Sophisticated atmospheric corrections routines now exist to remove atmospheric effects from the data acquired by passive sensors. Photographic passive sensors. The most common sensor system is a photographic camera, which is a simple passive sensor. Many of the historical developments in remote sensing were directly related to the development of photographic systems. Camera systems are similar in design to the human eye. Both have a lens at one end of an enclosed chamber and a light sensitive material, film for a camera and a retina for an eye at the other. In both systems, as iris is used to control the amount of light that can strike the film or retina. In a camera, a shutter is placed between the lens and the film to control how long the light can strike the film. Filters can be attached in the front of the lens to restrict the wavelength of light permitted to strike the film. Electro-optic radiometers. A radiometer is an instrument designed to measure the intensity of the electromagnetic radiation in a set of wave bands ranging from ultraviolet to microwave wavelengths. The radiometer discussed here are called electro-optic sensors because they measure electromagnetic energy using optical techniques and electronic detectors. Though they are only capable of recording a single data value for their view area. If they are mounted in a scanner device, images can be produced. Radiometers are similar in design to the camera in that they have an opening for the light to enter, lenses and a mirror for the light to pass through. But instead of film, they have an electronic detector to record the intensity of the electromagnetic energy. As energy hits the detector, a signal proportionate to the incoming irradiance is processed to either a digital or analog output that can be recorded. Detectors for radiometers have been devised to measure wavelengths from 0.4 to 14 micrometers. Although some radiometers can detect this entire range of wavelength, most only measure selected wavebands in this range. Radiometers that measure more than one waveband are called multispectral radiometers. For this type of radiometer, the light must be separated into discrete wavebands so that multiple waveband or multi-channel readings can be taken. This separation can be done using filters, prism or other sophisticated techniques. Non-imaging radiometers are commonly used as research tools to better understanding how light interacts with objects, for spectral characterization of variety of surfaces and for atmospheric measurements. Another common use is to measure the quality and the quantity of the solar energy. These measurements can be in turn be used to correct other imaging and non-imaging measurements for atmospheric effects. Active remote sensing. Active sensors are those which have their own source of electromagnetic radiation for illuminating the object. Radar and LiDAR are some of the active sensors. Some advantages of active sensors are they do not require solar illumination of surfaces or perfect weather conditions to collect useful data. Consequently, they can be deployed at night or in conditions of the clouds or light rains. The active remote sensing has more control of noise originating from the source of the electromagnetic radiation and reflection of the target through the control of the injected signal. Active remote sensing can be used for shallow look angles that create different target perspective, giving more accurate readings of the ground object. Active remote sensing allows for the radiation penetrating through vegetation in water bodies, soil and snow, and It is excellent in collecting Earth surface information and it is not hindered by any weather condition. Active remote sensing is helpful in flood mapping, geological data, volcanic eruption, earthquakes, disaster management, soil study and mapping of minerals. Active remote sensing can generate large quantities of data from various sources generating a detailed interpretation of the Earth's surface. Active remote sensing revolves around near polar orbits and has high accuracy in both lateral and longitudinal direction. Radar. Active microwave. Radar is a radio detection and ranging systems which uses microwaves, wavelengths ranging from 1 millimeter to 1 meter. Microwave pulses are transmitted at the target or the surface and the timing and the intensity of the written signal is recorded. The transmission characteristics of the radar depends on the wavelength and polarization of the energy pulse. Common wavelength bands used in pulse transmission are K band, that is 11 to 16.7 millimeter, X band, that is 24 to 37.5 millimeter, and L band 150 to 300 millimeters. The use of the latter codes to designate the wavelength range for various radar systems originated when radar was being developed during World War II. The random letter designation were assigned arbitrarily to ensure military security. However, their use has persisted. Distinct from wavelength is the polarization of the transmitted energy. Pulses can be transmitted or received in either an H horizontal or V vertical plane of the polarization. Factors determining the strength of the radar return signal are complex and varied. However, the most important are geometric and electrical properties of the surface or object that reflects the signal. Information about the structure and composition of the object and the surface can be detected by radar. Radar has been used in number of fields including geology, snow and ice studies, oceanography, agriculture and vegetation studies. Radar has been especially useful in areas with nearly constant cloud cover. LiDAR. Active optical. LiDAR is light detecting and ranging system, uses the laser light as an illuminating source. A short pulse of light is emitted from the laser and the detector receives the light energy, that is photons, after it has been reflected or absorbed or emitted by an object or surface. A LiDAR system emits pulses at specific narrow wavelengths that depend on the type of laser transmitted use. The possible wavelengths range from about 0.3 to 1.5 millimeters, which covers the ultraviolet through the near infrared spectral range. The simplest LiDAR systems measure the round trip travel time of a laser pulse, which is directly related to the distance between the sensor and the target. Basic distance measuring LiDARs are often referred to as range finders or as a laser altimeters if deployed on an aircraft or spacecraft. These systems typically measures elevation, slopes and roughness of land, ice or water surfaces. More advanced LiDAR measures the received intensity of the backscattered light as a function of the travel time. The intensity of the signal provides information about the material that reflected the photons. Such backscatter LiDAR systems are often used for atmospheric monitoring application concerned with the detection and characterization of various gases, aerosols and particulates. LiDAR method have recently been adapted to measure tree heights and vertical distribution of canopy layers with great accuracy and precision. LiDAR instruments have flown on the Space Shuttle and Vegetation Canopy LiDAR (VCL) and ice clouds and land elevation satellites (ISAT) LiDAR missions are planned for the near future. LiDAR systems are also make fluorescence measurements. Fluorescence refers to the process where the material absorbs the radiant energy at one wavelength and then emits it at different wavelength without the first converting the absorbed energy into the thermal energy. The wavelength at which absorption and emission occurs are specific to the particular molecules. fluorescence data can identify and quantify the amount of plankton and pollutants in the marine environment. Leaf fluorescence can also help in identifying plant species. Summary: sensor is an electronic circuit which can record the electromagnetic radiation incident upon it. Sensor systems mainly operate in the visible, infrared, thermal and microwave regions of the electromagnetic radiation. Sensors can be divided into different classifications. Imaging sensors are used in remote sensing data where the recorded representation of the radiation of the reflected or emitted from the object or an area is used. Non-imaging sensors usually have handheld devices that register only a single response value with no final resolution. Then the whole area viewed by the sensor, and therefore no image can be made from the data. Non-imaging sensors include radiometer, altimeter, spectrometer, spectroradiometer, etc. Passive sensors measure light reflected or emitted naturally from the surface and the objects. Remote sensing is preferred for satellite imagery since it delivers excellent image in quality technology such as hyperspectral and multispectral. Illumination for passive system is that most of the cases require sunlight in order to valid in useful data to be acquired. Active sensors are those which have their own source of electromagnetic radiation for illuminating the object. Radar and LiDAR are some of the active sensors. Active remote sensing is helpful in flood mapping, geological data, volcanic eruption, disaster management, etc. Active remote sensing can generate large quantities of data, whereas compared to the passive remote sensing, many satellites are equipped with passive sensor systems which are depending on solar illumination, and therefore the satellites orbit around the Earth. As they measure the reflection of sunlight from the Earth, their objects must be adjusted to the rhythm of the day and night. It is important to be able to compare images recorded over the period of time. If they are to be comparable, the light conditions must be identical. The recordings must take place at the same local time of the day so that the altitude of the sun above the horizon is the same and the plane of the satellite orbit must remain at a constant angle to the light from the sun. These prerequisites can be achieved by placing the satellite in a polar orbit. While the satellite is revolving in its orbit, the Earth rotates on its axis. Every time the satellite makes a complete rotation, a new strip of Earth's surface is scanned, and after the certain number of rotation, the entire surface of the Earth will have been acquired. Some satellites scan a broad strip every time they can, therefore cover entire Earth in few rotations, whereas high resolution satellites scanning only a narrow strip takes several days to complete the coverage of the Earth.